Hi, my name is Robert, and I'll be presenting joint work with Avi Wigderson titled Constant Depth Arithmetic Circuits for Linear Algebra Problems. The full version of this work is available on Archive, and if you're interested in learning more, there's a 2-hour version of this talk available on YouTube. This work is focused on computing greatest common divisors of univariate polynomials. So recall, if we have two univariate polynomials, f and g, with coefficients in some field f, then their greatest common divisor is simply the highest degree polynomial that simultaneously divides f and g. And the main question we'll be interested in is, if we're given the coefficients of f and g as input, how many arithmetic operations do we need in order to compute their GCD? So we'll be concerned with the number of additions, subtractions, multiplications, and divisions that our algorithm uses, but we may not necessarily care about the bit complexity of these operations. Why are we interested in computing the GCD? Well, this is a fundamental operation in computer algebra with numerous applications, including to algorithms for polynomial factorization, decoding of error-correcting codes, and so on. Now, as we all know, you can compute the GCD in polynomial time, and the Euclidean algorithm gives you a way to do this. A coarse estimate of the running time says that if you want to compute the GCD of 2 degree d polynomials, you can do this in roughly d cubed many arithmetic operations. Some more clever divide and conquer based ideas will give you an even faster algorithm that says you can compute the GCD with a near linear number of arithmetic operations. So not only can we compute the GCD in polynomial time, but we have a near linear time algorithm for this problem. Both of these algorithms are fantastic, but they leave potentially one thing to be desired, which is, if you look at these algorithms, they both appear to be inherently sequential. For example, the Euclidean algorithm takes f and g and computes a sequence of polynomial divisions with remainder, where the very last remainder in this sequence is the GCD. And it's not immediately clear that you can compute the GCD without having to compute all of these intermediate results. So there's a natural question here: is there an efficient parallel algorithm that we can use to compute the GCD? If you haven't seen this before, the answer might be a little surprising. In fact, there is a fast parallel algorithm to compute the GCD. So this is a result of Borden, von Sergatten, and Hopcroft, that the GCD can be computed with a polynomial number of arithmetic operations and in log squared d parallel time. And the idea behind this algorithm is beautifully simple. It's a reduction to linear algebra. What you do is you express the GCD as a solution to a system of linear equations, or maybe a solution to a collection of systems of linear equations. And then you invoke off-the-shelf efficient parallel algorithms for linear algebra problems, such as computing determinants and inverting matrices. I want to give you a little bit more details on what this reduction looks like. So to set some notation, we have two polynomials, f and g. The fi's are the coefficients of f, and the gi's are the coefficients of g. For simplicity, we'll only look at the case where we want to decide if f and g are coprime. We want to decide if they have GCD1. Now, it's a fact that you can prove using some algebra that two polynomials are coprime exactly when the following conditions hold. There are two other polynomials, s and t. The first two bullets say that s and t should be of low degree, and the third bullet says that we have an interesting polynomial identity, that s times f plus t times g equals 1, identically as polynomials. Now, if you stare at this for long enough, you realize that this third bullet point is actually a system of linear equations in the unknown coefficients of s and t. So how do we check if the GCD is 1? Well, we need to check if we can find these two polynomials s and t, which is exactly checking if this linear system has a solution. So we can do this with an off-the-shelf parallel algorithm for solving linear systems. In fact, this system has even a little bit extra structure. It doesn't really depend on the right-hand side, in the sense that the GCD is 1 exactly when the left-hand side coefficient matrix is invertible. So this is another characterization of when two polynomials are coprime. You look at the left-hand coefficient matrix of this linear system, which, when you write it down, looks like this. You have one parallelogram formed by the coefficients of f, and you have a second parallelogram formed by the coefficients of g. And you want to check if this matrix is invertible, which is the same as checking if its determinant is non-zero. And this is actually a very well-studied quantity in algebra called the resultant of f and g. This has been investigated by mathematicians for well over 100 years. So what's the punchline of all of this? If you want to decide if two polynomials are coprime, all you need to do is write down this matrix and check if it has a non-zero determinant. And now you can invoke a parallel algorithm for computing determinants. For example, we know that you can compute a determinant using an algebraic circuit of polynomial size and log squared depth. And here the depth of the circuit will correspond to the running time of your parallel algorithm. So this gives us a log squared time algorithm to check if two polynomials are coprime. What if we want a faster parallel algorithm? Well, we can't necessarily use linear algebra because this log squared depth is suspected to be optimal for generic linear algebra. In general, we think that to compute an n by n determinant with a polynomial-sized circuit, you probably need log squared depth. So if we want faster parallel algorithms to compute something like the GCD or to check coprimality, we need an approach that is qualitatively different from using linear algebra. So before I tell you about our results, I just want to make the model of computation clear. So we're working with algebraic circuits in this paper. These are circuits that are built from addition and multiplication gates. They take as input formal variables, and they output a polynomial. So for example, the circuit on the slide takes as input the two variables x and y, and outputs the polynomial x squared minus y squared. We'll measure the size of a circuit by the number of wires appearing in it, and we'll measure the depth of the circuit by the length of the longest path from an input to the output of the circuit. Okay, so now that it's clear what model of computation we're using, let me tell you about our results. So I'm going to state our results for polynomials with complex coefficients, but our results hold equally well over any field of characteristic 0 or of sufficiently large characteristic. So given two polynomials f and g of degree d, here's what we can do. We can compute their resultant, which is this structured determinant that tests coprimality we saw a few slides ago. We can also compute their GCD. We can compute polynomials s and t that witness the GCD. These are sometimes called the Bézieux coefficients of f and g. And we can also compute what's called the square-free decomposition of f and the square-free decomposition of g. And if you don't know what this is some structured partial factorization of the polynomials f and g. We can compute all of these using algebraic circuits of polynomial size and of constant depth. And because our circuits have constant depth, they'll necessarily have unbounded fan-in. Now I want to mention there's a bit of an asterisk here, because some of these results, well, algebraic circuits just aren't strong enough as a model of computation to compute something like the GCD. You need to extend the model of computation just a little bit, and it turns out what you really need and what suffices is to have a branching instruction that lets you take a quantity you've already computed and test if it equals 0 or not, and then branch based on if that quantity equals 0 or if it does not equal 0. In this talk, we won't see why this branching is necessary, but it turns out that mathematically you just need an operation like this to compute something like the GCD. So these are our results. I want to give you an idea of what are some of the tools we're using to design these circuits, and what do the algorithms actually look like. So we really only make use of two tools in this paper, and there's an argument to be made that there's actually only one tool. And that one tool really is polynomial interpolation. So, of course, if you ever have a multivariate polynomial, you can single out one of the variables and write this polynomial as a univariate in that variable, where the coefficients are polynomials in the remaining variables. So for example, if I have this multivariate polynomial f, I can always write it as a univariate in y, with coefficients being polynomials in the x variables. Now, what can we do here? Well, suppose we have a small, low-depth circuit that computes f. We have a circuit of size s and of depth delta. Well, we can use this circuit to find similarly small, low-depth circuits for these coefficient polynomials fi. So what you can do is, for each I, you can compute the coefficient fi in size roughly s times d, here d is the degree, and in depth delta plus 1. So the size of your circuit blows up by a factor of d, which is tolerable, and the depth increases just by 1. And how do you do this? Well, this is polynomial interpolation. You can always recover the coefficients of a polynomial as a linear combination of evaluations at a sufficiently large number of points. So you can duplicate the circuit for f, evaluate it at different values of y, and then take an appropriate linear combination. This gives you the fi's. Now, what can you do with this? Well, I want to give you an example of how you might apply interpolation, and in order to do that, I need to introduce one family of polynomials that plays a crucial role in our work. These are the elementary symmetric polynomials. So these are polynomials in n variables of degree d. And what are they? Well, you sum over all size d subsets of the integers 1 through n. And for each subset, you pick up a monomial, which corresponds to the variables indexed by that subset. Why are the elementary symmetric polynomials relevant to our situation? Well, it turns out they kind of correspond to the coefficients of univariate polynomials in the following sense. Say I have a univariate polynomial f over the complex numbers. I can always factor f into linear factors. So I can write f as the product x minus alpha I goes from 1 to n, where the alpha i's are some complex numbers. I don't necessarily know what they are, but mathematically, of course, we can write f like this. If you expand out this product, you see that the coefficients of f are up to a sign which we can easily determine. The coefficients are really the elementary symmetric polynomials evaluated at the roots of f. And this is important. We should really think of the coefficients of f as being the elementary symmetric polynomials evaluated at the roots. So here, now I'll give you an example of how we can apply polynomial interpolation to design interesting circuits. So there's a lovely result by Michael Ben-Or from the 1980s that says you can compute these elementary symmetric polynomials with circuits of depth 3 and of quadratic size. And this might appear a bit surprising because these polynomials have an exponential number of monomials. It's not exactly clear how you can arrange for all these monomials to appear with the correct coefficients using such a small circuit of very low depth. But, the algorithm here is really just interpolation. If you look at this product of 1 plus y times xi, and you expand as a univariate polynomial in y, you see that the coefficients are exactly the elementary symmetric polynomials. So you apply interpolation in the y variable, and this gives you a small low-depth circuit that computes the elementary symmetric polynomials. Now I want to introduce you to a second family of polynomials that plays a crucial role in our work. And these are the power sum polynomials. They have a very simple definition. I have n variables, degree d, and what I do is I take the sum of the dth powers of the variables. Now, why are the power sums interesting? Well, one reason you might be interested in these is because of the so-called fundamental theorem of symmetric polynomials, which says the following. For every symmetric polynomial f, I can find another polynomial g. G may not itself be symmetric, but I can write f as g composed with the power sum polynomials. Now, the power sums are obviously symmetric polynomials themselves, so this g composed power sums is also obviously symmetric. So in some sense, what this says is if a polynomial f is symmetric, you can explain the fact that f is symmetric using the power sum polynomials. There's an analogous version of this theorem that holds with the power sums replaced by the elementary symmetric functions. So in particular, this says there's some kind of conversion between the elementary symmetric polynomials and the power sum polynomials. So there's a natural question here. Can we make this conversion between these two families of polynomials explicit? And this leads us to our second tool, which are known as the Newton identities or the Newton-Girard identities. We make crucial use of these. So it's a fact that I don't want to explain in great detail here that there are explicit low-depth identities that relate to the elementary symmetric functions and the power sum polynomials. Now, using this fact, you can design circuits that do something interesting. They convert between these bases in very low depth and in small size. So for example, if you're given as input the power sum polynomials, you can from those compute the elementary symmetric polynomials in polynomial size and in constant depth. And the way you design this circuit is you use one of these explicit identities and you apply polynomial interpolation. And the other direction holds just as well, that if you're given as input the elementary symmetric polynomials, you can compute the power sum polynomials in polynomial size and in constant depth. And one thing that's interesting here is the power sums are defined in degrees above n. Even if there are just n variables, you can of course look at degree 2n, n squared, n cubed, and so on. And this algorithm allows us to access all degrees of the power sum polynomials, and this will be important for us. So really, the takeaway from this slide is that you can efficiently convert in low depth between the elementary symmetric functions and the power sums. So how are we going to use this? Let me give you an example. This is a bit of a warm-up problem. So say we have two polynomials, f and g, and we're given the coefficients of f and g. Now we're working over the complex numbers, so f has roots alpha 1 through alpha n. What we want to compute is we want to evaluate g at each root of f, and we want to sum these evaluations. Now, of course, we're given the coefficients of f as input. We're not given the roots of f. So it's not immediately clear that, you can do this, but as it turns out, you can compute this sum in polynomial size and in constant depth. And here's how you do this. It's a two-line algorithm. First, remember the coefficients of f are the elementary symmetric functions of these roots alpha 1 through alpha n. So using Newton's identities, we can actually compute the power sums of the alphas. Now, we still haven't learned what the alphas are, but we have their power sums. And now if you look at this summation that we're trying to compute, you expand it and change the order of summation, you realize it's an inner product between two vectors. The first vector is just the coefficients of g, and the second is the vector of power sums of the alphas. So we can just compute this by adding two more layers into our circuit and a small number of gates. This gives us a polynomial size constant depth circuit to compute this sum. Now, it's not immediately clear why this sum is an interesting quantity to compute or what it's useful for, but now let's generalize this a little bit, and we'll start making progress towards something like the GCD. So now we can generalize this and say not only compute the sum of the g alphas, but in fact we can compute any elementary symmetric function of the g alphas, again in polynomial size and in constant depth. How do we do this? Well, it's a simple extension of the algorithm from the previous slide. The first step, we're going to interpolate the coefficients of powers of g. So we'll get the coefficients of g squared, the coefficients of g cubed, g to the 4, all the way up to g to the n. Then what we'll do is, using the algorithm from the previous slide, we'll compute the power sums of these g alpha i's. Now, because we have the power sums in these quantities, we can use Newton's identities in the other direction, and from the power sums, compute any elementary symmetric function that we want. So this is all nice, but it's not exactly clear why this is useful for computing something like the GCD. So let me, now bring it back to the GCD and show you that we've actually already made useful progress. So I want to remember this interesting determinant we saw earlier, the resultant of f and g. Remember, it's a structured determinant that tells you if two polynomials are coprime. Now, of course, this is one way to write down the resultant, but it's not the only expression for the resultant. So there's another expression that turns out to be very useful for us. So you can show that if f has roots alpha 1 through alpha n, then the resultant of f and g is exactly the product of the g alpha i's. And this is actually a very you would expect this to be true, because if f and g are coprime, this means that g does not share a common root with f over the complex numbers. So all these g alpha i's are non-zero, the product is non-zero. On the other hand, if f and g do share a common factor, well, they share a root over the complex numbers. So one of the g alpha i's is 0, so the product is 0. Now, what's interesting about this identity is this product of g alpha i's is precisely the degree n elementary symmetric polynomial of the g alpha i's. So we know how to compute that in constant depth and in polynomial size. So now we have our first theorem. Given the coefficients of f and g as input, we can compute their resultant in polynomial size and constant depth. Even though the resultant was defined as a very structured determinant, it turns out there's a different way to approach computing it that gives you a much lower depth circuit. Unfortunately, I don't have much time, so I can't tell you about all the details that go into our GCD algorithm, so let me just end with a few open questions left by this work. So the first question is, we have this fast parallel algorithm to compute the GCD, but one thing we can't handle is what's called the extended Euclidean scheme of two polynomials. So if you look at the Euclidean algorithm, it computes a sequence of remainders and it computes a sequence of Bézout coefficients. Can we compute all of those remainders and all of those Bézout coefficients in, say, polynomial size and depth lower than log squared? It's not exactly clear how to do this. And for those of you who are experts on this, one thing that we don't even know how to handle are what are called subresultants. So these are structured determinants that look like the resultant, but they appear to be somewhat more complicated. So it would be really nice to get faster parallel algorithms for these problems. And then a second interesting question that we don't really know how to handle is, it seems like everything we're doing in this work is really about understanding symmetric polynomials and what symmetric polynomials can be efficiently computed in low depth. And we want to understand this from a more structural perspective. So here's a very simple form of this question that we don't know how to answer. Say you have a symmetric polynomial f. You can always write it as g composed with the elementary symmetric polynomials. Suppose f has a small depth 3 circuit. Does g have a small formula? We don't know how to approach this, but it would be interesting to answer this question in either direction. So that's all I want to say. Thank you so much for stopping by.